Oh, 10.
10.
Just sit there or?
Yes,
I mean,
okay.
Or
you can sit.
need me here.
No, we can
It's
sit.
advisable if you stand, but
Huh?
it's advisable if you stand. You can sit if you want.
That's, huh? Right.
You have to stand that way because of the camera.
Yeah. Here?
Hello, everyone. I hope you can hear me well. My name is Stoyan, and today we're going to talk about effortless concurrency with ArrowFX on Android. I'm a software engineer at Axel Springer. I basically build a newspaper app, and I do mostly Android and a little bit of backend work, and as we have server-driven UI. Okay, sorry about that. So, the agenda for today. We're going to introduce a small example. Hopefully it's realistic enough, and all of you may have done something similar in the past or will do in the future. Then we're going to do a simple solution using plain coroutines, as in the Kotlin X coroutines library. We're going to optimize it with the Kotlin X coroutines library. Then we're going to introduce Arrow and see if there are some functions there that can help us solve the problem in an optimal way. And in the end, we're going to wrap up with talking about Arrow schedule, which is helpful for resiliency. This is the app we're going to work with. There is a free API called DocCU API, and it offers a few endpoints. In this scenario, we are showing a list of dog breeds, and for each dog breed, we're showing a random image. The UI is built with Compose, but it's not really relevant here. So the API we're going to work with has a few endpoints. One of the endpoints is list all breeds, which basically gives us a list of all dog breeds that are available. As we can see, there is no image here. We only get the names. To get the images, we need to do a second API call. And that API call is random image from a breed. Given a breed name, it will give us an image URL. A Kotlin API for this would look something like this. We can have a breed names function, a suspend function that returns a list of strings, and each element in the list will be the breed names from the API. And we can have another function, suspend function, image URL, that takes a breed name and returns a pair where we have the name and the image URL for the given breed. And to solve our problem, we will need to call the first function, and then for each element in the list, call our second function. And if we want to do the simplest solution we can get away with, it would look something like this. We call our breed name function, and we get a list back. We use the map operator that's executed for each element in the list, and we call the image URL. Because map is inline, this will work, but it has like a slight problem. We have a lot of dog breeds. So it's very, very slow. These are some durations on my machine when I was working on preparing this talk. It takes around 20 seconds. And ain't nobody got time for that. So how can we optimize this? I once tried to explain optimizing this to a friend over a phone. And basically the solution is opening a coroutine scope. We use async to start some child coroutines, and we get deferreds back, and we call await all on those deferreds. And things should just work. And if you're listening to this over the phone, you might implement something like this, where we call the breed names, we use map, we open a coroutine scope, and we call async inside it, and then we call await all on the resulting deferreds. However, this is even slower than the previous one, because it's wrong. The actual solution that we want is something like this. we open exactly one top-level coroutine scope. Inside it, Brit names actually can be also outside, it doesn't really matter, but inside it, we call map and async to start child coroutines, and then we call await all. And this takes roughly 5 seconds to execute everything, which is much better than the original 20 seconds. How does this work? It will execute the image URL function concurrently. That means that depending on the dispatcher, it might get executed in parallel. If you're using something like retrofit, it already has its own thread pool, so it will be executed in parallel. And if one of the child coroutines fails because of an error, basically if it throws an exception, it will cancel the rest of the children, and the whole computation will fail. And this is something that's probably desirable by default, because if you want a list of 20 items and you only get 19, it would be confusing, unless it's what you're intending to do. And we will go on more specific error handling a bit later. Let's talk about Arrow a little bit. It's a set of libraries that are inspired by functional programming communities and that are adapted to Kotlin-friendly way. It has multiple libraries, like Core, ArrowFX, Arrow Resilience, Arrow Optics. I think there are a few more. Arrow Core contains some utilities around typed error handling, and it has some DSLs that make working with the errors in a type-safe way. We will not be covering that today. ArrowFX has some utilities for working with coroutines, mostly around parallel execution and other stuff, also with flows. Arrow Resilience has things like circuit breaker and schedule. Today we will talk a little bit about schedule. Arrow Optics helps us working with deeply nested immutable data types. It basically can provide a copy function that works really nice with deeply nested data classes or sealed classes. So let's take a look at how we can solve our problem using ArrowFX. We have a function, ArrowFX. It returns a list of a pair with a breed name and an image URL. And we call our breed names function from the original example that returns the list. And then we use, instead of map, that will call the image URL function sequentially, we use parmap, which will call them concurrently. Internally, this works in the same way as the optimized coroutines example. And we only did one function change to go from sequential to parallel. We went from map to parmap. I think I could explain this over a phone and nobody would get it wrong. So the main benefit here is less error prone. So what do we do if we want to, let's say, change the error handling and ignore some errors? Let's say a dog has no image, API trolls. If that happens, one way to handle it is to remove that breed name from the list and just show the remaining ones that did succeed. With using just the Kotlin X coroutines library, we could adjust our function like this. We still open the coroutine scope at top level. We still call our breed names function. Here we're not doing any error handling because if that fails, there is nothing to show. And for the image URL, we do a try catch. And if it fails with an error exception in this example, we return null. We still do the async stuff, so ticks are executed in parallel. And we still do await all. to wait for all the computations and extract the URL from there. And since now we get a list of nullable elements, we can add filter not null to remove all the null elements from the list. Doing the same with arrow would look like this. Instead of par map, we would use par map not null. The naming is inspired by the Kotlin X standard library, where a list has a map operator and a map not null operator, where map not null is like map and filter null. Similarly here, we can use par map not null, and any nullable elements in the list will be filtered. So we call breed names, we use par map not null, we do our usual try catch for the image URL function, and return null in case there is an IO exception. And this works in the same way as the previous example. Another thing we might want to do when working with this is if we notice that the breed names has a lot of breed names, and maybe the server starts slowing down if it gets a lot of concurrent requests. Another common thing might be to limit the number of concurrency. So we went from 1 to infinity. Maybe we want to do something like 5, 10, or 25, or whatever number. To do this, the Kotlin coroutines library offers the semaphore data type, and limiting concurrency to something like 10 would be as simple as creating a semaphore inside our function. And then when calling our image URL function, we use the semaphore with permit function to limit the concurrency. The way this works is it only allows up to 10 requests at a time, because we have 10 as the concurrency limit. Otherwise, it works exactly the same. If we want to do the same thing with arrow, conveniently, arrow offers a parameter concurrency that has some default value, and we can set whatever number we want there. Internally, this is exactly the same code as the previous slide. It uses a semaphore internally. And other things that we can adjust also is the dispatcher in which the Lambda runs. I don't have an example for that, but it's also possible to set it. So far, we've been talking about working with lists of functions for computations. Now we're going to switch topic a bit and talk about independent computations. So we had a list, and every function in that list was from the same type. We're going to introduce an example now that's not supported by the API, but it's just like to explain a concept. We want to get a random image for a breed once we have a name, and we can also get a fun fact, something fun about that breed. This doesn't exist in the API. We can, of course, do the boring thing and do it sequentially. It's probably not going to take 20 seconds because it's just 2 API calls, but the topic today is let's do it really fast, or as fast as possible. The Kotlin API would look like shown here. We have the same image URL function that takes a breed name and returns its name and an image URL. We also have a fun fact function, which is a suspend function, and returns a string. This is the fun fact. Using plain Kotlin X coroutines, it's again the similar approach where we open our coroutine scope. Inside it, we can use async to create a deferred. The first deferred will get the image URL. The second deferred would get a fun fact. And then we can create a pair from both of them, and we call await to get the underlying value. And this works well, but it kind of obfuscates the logic a little bit. We have this coroutine scope, we have these asyncs, we have these variables that are introduced that represent the deferreds. Ideally, we would want to focus on image URL, fun fact, and how we combine them together, which is basically the last line. And to do this, Arrow offers a function called parzip. So given a breed name, our function here execute will return a pair of the image URL and the fun fact for the breed. We can use parzip from Arrow, and we pass it two lambdas. The first one is image URL, and the second one is breed fun fact. And we have a third lambda that specifies how we combine the results of the first two lambdas. And here we are using the to operator to create a pair from the image URL and fun fact. And how this works. It executes both functions concurrently. Same as previous, if the dispatcher supports parallelism, it will be executed in parallel. It executes the lambda only if both computations succeed. This makes sense because the lambda is executed with the result of both computations. So we need both of them to succeed for the lambda to be called. There are actually overrides with more than two functions, so it doesn't have to be two. It can be 3 or 4, I don't remember the max limit. And similarly, a failure in one action cancels the other action. So if I go back, if image URL fails, breed fun fact will be canceled because it doesn't make sense to execute it if we know that the whole thing is going to fail. This helps in conserving resources, which I guess is useful on Android. Yeah. Let's talk about racing. It's another functionality offered by Arrow. And a motivation for racing might be that if we want to introduce some local caching, if we notice that the breed names rarely change, so maybe we want to cache them for a few hours locally on the device, so the whole thing, again, is faster. And we want to get the data from the cache. If the cache is empty, only then we call the remote. If the remote call works, we want to save the result in the cache so that we can reuse it the next time we call our function. And a simple solution to this would look like this. We have a function breed names that returns the list of breed names. We first try to get the cached breeds that returns a nullable list. And if this is null, we will call the remote breeds that calls the backend. And then we return the result. And this works assuming that cached breeds will be super fast and remote is typically slower. However, there is a slight problem here. It actually makes, in the worst case, the breed names function to perform slightly slower because we are always trying to get from cache first, and that takes a non-zero time. Ideally, that will be super fast, so it won't be noticeable, but the topic of today is make it as fast as possible. And let's see how we can do that. So we can use the race n function from Arrow, which basically takes 2 or 3 functions. There's overloads for 2 or 3 functions. And it will concurrently run both of them. So it will concurrently run cached breeds and remote breeds. As soon as one of them completes, it will cancel the other one. Meaning there is one winner and the rest of the computations are canceled. That means that if the cache is empty, both functions start at the same time. And here I have a note that if the cache is empty, this one should never complete. And remote breeds will complete in, I guess, around 100 milliseconds. Let's say that's the API response time. The first one will get canceled, and we get the result of the second one. If the cache is full, again, both computations start at the same time, and hopefully the cache is super fast and it wins. The remote call will be canceled, and we get the result from the cache. Here we have also merge because the result return type is either, and we have list of strings on the right, list of strings on the left, and we merge the results together because it's always a list of strings. That's from the Arrow core library. You can check about it in the documentation. Here we wanted to focus on race. ArrowFX offers a bunch of other functions that I'm not going to discuss in details. For example, we saw that parmap will fail in case any computation fails. Sometimes that's not desirable. Parmap or accumulate would, again, fail the computation if one of the requests fails. It will fail the resulting computation, but it will execute all requests and collect all errors. This might be useful for form validation or some similar use cases where we still want to, or if you're syncing data to backend, and you might want to get all errors and then retry only the things that failed later. Similarly to parmap on a list, we have parmap on a flow. And here the resulting flow that's transformed will conserve the ordering of the elements as the original flow. And there is flow.parmap unordered, which doesn't guarantee preserving the elements. It will emit the new flow as soon as the computations complete that are passed to the Lambda. That was all about ArrowFX. Now we move into Arrow resilience. Specifically the schedule data type. It allows us to compose powerful yet simple policies, and we can use those policies to either retry or repeat computations. The reasons we would like to repeat computations are because they failed, and the reasons we want to, repeat in case of success, and we would like to retry if they failed. And the scheduled data type is an abstraction that allows us to define how many times we repeat, how long we wait between repetitions. The library offers some built-in schedules. For example, schedule.recurse. It's a policy that runs up to n times. In this example, I have 10 as the parameter, so it will run up to 10 times without a break between repetitions. We have schedule.spaced with a duration as an argument. A policy that repeats, that runs forever, but it takes 60-second breaks. We have schedule.exponential. We can customize it with a base duration, and it will do an exponential backing off in the runs. We have schedule.fibonacci, same idea, but Fibonacci numbers. Schedule.linear, and much more. Now, we can use these as they are, but maybe they're not very useful as they are, or we can use some combinators to combine them and build some more complex schedules. Some of those combinators are AND, that takes two schedules and runs if both of them want to run. That means it will run only if both of them agree that they need to run. and it will take the longer duration between their breaks, individual breaks. We have a do while that takes one schedule, and based on the duration, it can execute a predicate and decide if we want to continue running or stop. We have and then, which enables us to sequence the schedules. You have one schedule, you run it until completion, then you take a second schedule and you run that one until completion. Jittered is a function that takes a schedule and runs and adds a random noise, so it can slightly increase or decrease the duration. This is useful if you don't want to overload your backend in case there is like a deployment error or something. You want to add some random delay so you don't DDoS your backend from all your clients. Let's see some examples of how this can be used. First, the end combinator. In this example, we take a spaced schedule with 60 seconds break and a schedule that repeats 10 times, and we combine them with end. The resulting schedule will run with 60 seconds delay for up to 10 times. So it's taking the delay of the longer, which is 60 seconds. Between 60 seconds and 0, the bigger one is 60. And it's taking the lower number of repetitions, which here is 10. So this is much more useful for practical applications. Do while. If we have an exponential schedule that will repeat exponentially forever, maybe we want to limit that to some reasonable amount of time a user will wait, something like 60 seconds. So here we use the do while operator, and we provide a function that returns true only if the resulting duration is less than 60 seconds. So we start with the 10 milliseconds exponential backing off, and as soon as the next break would come up to 60 seconds, it will give up. Another one is and then. So this basically allows us to chain schedules together. When the first one completes, it will run the second one. And here we're putting together the two complex schedules from the previous slides into one. We have an exponential backing off with 10 milliseconds delay. We cap that to a maximum of 60 seconds using do while. We use and then to chain that with a space schedule with a 60 seconds delay that repeats up to 10 times. And in the end, we add a random noise so we don't overload the backend. And we can use this schedule both for retrying actions or repeating actions. For example, if we have our spaced schedule that repeats up to 10 times, we can use schedule.retry, and it will retry the breathe images function as long as it's failing or the schedule reaches its end. Similarly, we can repeat actions. I'm not sure why we would want to call this function 10 times in a row or something, but it is possible. This is more useful for, let's say, you want to periodically send a location update to your server or something like that. This is a really interesting data type that's inspired from Scala. The Arrow version is a port from Scala. And there is a full talk by the original author on YouTube available that you can watch if you want to hear more about the inspiration. Now that we learned a bit about Arrow FX and Arrow resilience and the scheduled data type, we can put all the stuff together. We can go back to our original function and implement it with parallelism, error handling, and retries. And that will look very similar. We have the same signature that returns a list of a pair of a breed name and an image URL. We call the breed names function. We use parmap not null to concurrently call the image URL function. We can also adjust the concurrency here if we wanted to. And then inside of the Lambda, we can use schedule.retry with any of the schedules we saw before and call the image URL function. If the schedule runs, or if the schedule finishes and the function still fails, we can return null. And because we have parmap not null, we filter out the null results. In conclusion, we can work with lists and concurrent operation using parmap. We can adjust things like concurrency and dispatchers that we want the functions to run. We can use parmap not null if we have nullable computations. When we have independent computations, we can use parzip. It has multiple overloads with any number, with different numbers of computations that we can run in parallel. For racing, we can use the raceend function. This is one use case is caching, but there are probably other use cases. And for resilience, we can use the schedule data type that has some built-in simpler policies and a bunch of combinators that allows us to combine them in complex and more powerful policies. That's all for today. Thank you for your attention. The QR code leads to the slides, which are available on GitHub. The repo is private for now. I will publish it soon. Thank you again. I'm not sure if the actual retry function is
Can we start? You can hear me? All right. We were waiting for you. All right, let's get started. Thank you for coming here today for this session about seamless mobile real-time communication with the WebRTC. Just a few people more, yeah. So during this session, we are going to talk about WebRTC and how to use it in a mobile app specifically. But before that, if this works, yes, let me introduce myself a bit. So my name is Rino. I'm a freelancer. I'm based in Paris. I'm also part of and a member of the Paris Android user group. First time in DroidconLisbon for me, so I'm very proud of being here today with you. Why this talk? I had the opportunity last year during a freelance mission for a client in video games, actually more cloud gaming, to work on WebRTC. So last year during the mission, I was able to set up a Compose multi-platform application or project and deploy it in a gaming solution for cloud gaming using WebRTC. I discovered things, and this talk is about sharing the things that I discovered. A bit about WebRTC first. WebRTC stands for Web Real-Time Communication, and it's a technology that enables real-time communication directly in your web browsers or your mobile application. The development and adoption of WebRTC has marked a significant evolution of web and communication technologies. With WebRTC, peers actually can stream video, audio, or even arbitrary data, binary data, which is very useful for cloud gaming when you send, for example, arrow up or left or right, this kind of data. First, the WebRTC, it's great to understand its history. So let's have a step back a bit and let's look at how the story began with WebRTC. In 2009, the concept of real-time communication within browser and without, yeah, you can join, and without the need for plugins started gaining traction around 2009, 2010. And Google played a significant role in that period. They acquired global IP, GIPS, in May 2010, and it was a company known for developing high-quality voice and video processing data. In May 2011, so Google announced the WebRTC project, and it open-sourced its key components. This move was just to make it standardized, so a technology that has standard, and it make it freely available to developers and inside browser vendors. So the W3C, the World Wide Web Consortium, and the IETF, the Internet Engineering Task Force, began working together with Google, of course, and also you will see some big companies, on working on a standard and making sure that the API and the protocol are all standardized, respectively. The W3C focused on the JavaScript API, and the IETF work on the underlying layers of the protocol and the data formats. It's working? Yes. 2012, Mozilla and Google started implementing the WebRTC inside their browsers. Firefox, Chrome, and this period marked the beginning of the practical experimentation and usage of WebRTC in real-world applications. 2014, WebRTC began gaining traction in the industry. Various startups and also established companies integrate WebRTC inside their solution into their product for video conferencing. File sharing also on real-time data exchange. In 2015, that technology matured with improved stability and performance. We discovered services like Appier.in, or now it's known as Whereby, if you heard of this software, and a lot of video conferencing tools showcasing WebRTC, like Google Meet. 2018, the W3C published the WebRTC standard 1.0. It marked a significant milestone in the development of WebRTC. So by that time, WebRTC was already seen widespread adoption in various domains, including the telehealth, online education, some customer support, and other social media. I have to. 2020, sorry, until now. So of course, there was the COVID. The COVID pandemic accelerated the adoption of WebRTC because the demand for remote communication skyrocketed. So platforms like Zoom, Google Meet, Microsoft Teams, for example, they saw a massive usage of leveraging WebRTC inside their offerings. That was the part of history. So now let's speak about how does it work under the hood, the architecture. How is WebRTC architectured? And let's dig a bit into the standard and the way things are working with WebRTC. But for that, we have to understand architecture with several clients. You might have heard of mesh architecture. So in a mesh architecture, all participants are directly connected to all other participants. So this solution has some advantages. It's easier to set up with a low operation cost, and it requires high bandwidth, which is a disadvantage. It requires high bandwidth for each client to make sure that they all communicate together. In a graph theory, a graph where each node is connected to everyone, it's called a complete graph. So you can see this kind of graph here with 3 clients. For a complete graph with n nodes, 3 here, there is this formula n multiply n minus 1 divided by 2. So you will see that it keeps increasing. So this model is not scalable if we're all of us connected inside this room. So that's great when you're calling one person or 2, but then we have to switch to another architecture. This is the multi-point conference unit. You have client A, client B, client C. What the solution is to put a server and then to connect directly them inside the server. So this solution requires high computational cost for decoding and encoding on the server side the stream and then dispatch it to all the other clients. It brings high latency at large scale because you have to have a server that is strong enough to dispatch all the stream. So for WebRTC, how does it work? So we have seen mesh, we have seen the multi-point. Let's say we have client A wants to talk to client B and we have a server on top. So the client A, he creates an offer, which is kind of its ID, and to a signaling server. The signaling server will relay it to client B, and the client B, as you have seen, receive the offer, which consider this as his ID. Then the client B creates an answer, send it to the signaling server, the signaling server relays it to client A, and client A receives the answer. So after that, since they know each other, they are going to send what we call ICE candidates. It's ICE candidate exchange between the client A and client B through the signaling server, and both are actually gathering their ICE candidates information. So it's basically how are we going to talk to each other. Once this is done, the ICE candidates are sent to the signaling server related to each other peers. So now we have client A and client B in a peer connection. We don't need the server anymore. Nice animation. So basically, to my opinion, the process of establishing a WebRTC connection between 2 peers can be divided into 2 major phases, as you have seen here. First, the signaling phases. This is the phase that involves the exchange of connection information, when I was saying about the ID, for peers to connect directly. So this phase is not handled by the WebRTC standard itself. We're going to see that after. It requires an external signaling server or mechanism that we can actually create ourselves, so it's not part of the standard. And then there is the peer-to-peer connection phase. So this is the phase that involves the actual establishment of the peer-to-peer connection, enabling media and data flow directly between the peers. We spoke a bit about ICE. ICE stands for Interactive Connectivity Establishment. It's a technique that combines two things, a stun and a turn server to discover and also to establish the best connection path between WebRTC peer connection or WebRTC clients. This is where it enables real-time communication and challenging also the network environment. If we are not on the same network, for example, or if I'm speaking to someone in South Africa, for example, from Asia. So it involves the stun, which is basically a protocol that is used to discover the public IP address and also the port of a client. And then we have the turn server that act intermediaries when direct peer-to-peer connection are not possible due to restrictive network configuration. So basically the stun and the turn relay media streams between the clients, and also they ensure that there is a reliable connection. So this is the complete graph of the architecture. So basically you have the NAT here that goes to the stun server. I think I can pin some, yeah. And also go to the turn server, the stun server. So you might have heard of Google is actually providing a turn server. There is also Twilio that you can use for free to discover the public address. Some information I would like to share before that. So the specification of the API, as I said, we have the specification of the ICE server. We do not have in the standard the implementation of the signaling server. It's not part of the standard. The WebRTC also transmit data using UDP, so the user datagram protocol. UDP is connectionless. That means that there is no formal connection between data transmission, and also the packets are independent, can be sent to any route, and also we don't have acknowledgement. So we can lose some packets sometimes using UDP. That's something that's important to share when using WebRTC. If you want to have fun and go on a Google Meet or open a WebRTC connection, I found that there is this link that you can directly open in Chrome, and you will see everything that is happening between your WebRTC connection. That's very useful to better understand what is coming under the hood. Okay, so as we have previously seen, the signaling server is not part of the standard, but also it's mandatory to establish the connection between two peers to make sure that they are going to connect. Usually, a signaling server is solved or created through a regular HTTP-based API. We can create a REST API or whatever RPC mechanism that we want. So basically, the web application can relay the necessary information before the peer connection is installed. This is the diagram. Sorry, it's something that I try to generate it, so it's not perfect visually, but it's how it works under the hood. So basically, client A speaks to the signaling server to initialize the WebRTC, client B as well. Then we create the offer that we have seen before. We're going to set within the standard our local descriptor to generate an offer. We're going to send the offer. The signaling server will relay the offer. The client B will receive the offer, set his remote description from the offer, then create an answer, set the local description from the answer, send the answer. The signaling server will relay the answer, then we receive the answer. So at the moment, it's not so complex. It's a lot of coming up and back. Then that's the phase with the ID I was talking about. And then the second phase is about the ICE candidates. So the signaling server will receive your ICE candidates, relay them. So client A and client B will both receive the ICE candidates from the relay server. And when it's done, and when we had that, when we had that, then we are able to establish a pure connection between client A and client B, and we don't need the signaling server anymore. The truth is, actually, when you see this diagram, you're like, okay, why we are not able to achieve this? So why not achieve this together as Kotlin engineers? So I suppose, sorry, but why not create our own signaling server together right now, so you can better understand how to establish a connection between client E and client B. So for those who know, I'm quite fond of Ktor. Might have, maybe it's shared with some of you in the room. So let's write this in Ktor, since we are Kotlin engineers. If you want to learn a bit, I wrote some articles about Ktors, how to set up a web server using Ktor, if you want to see that. I also put some article about Material 3 if you don't want to do backend. So let's go and start to create our signaling server. Let's go to startktor.io, and for that, it's better to have a WebSocket because it's fast and easy to set up. So I had the plugin WebSocket. We will also need, we will see later, but it's more for scalability, encoding and serialization. So we are going to use the serialization from Kotlin X. So I add it as well. Now this is from the field. What we could do is, okay, the client is sending me some text. Why I'm not distributing it to the client? Client A is sending me some text. Why I'm not sending back to client B? Just plain text. Actually, you will see that it could work, and we're going to see that it works, but it's better to wrap everything inside what I call WS WebSocket. You can call it whatever you want, but wrap this inside a packet. So what I'm going to do, what I did actually, is you put an ID with the messages and also the data as a string, and you wrap and you make sure that it's always WS packet or your interface on top. And the WS messages is for now an enum. We have errors when we gather the ICE candidates, ICE server, the init, answer, offer. So this is for now what we need. Also, signaling server. What we would like to achieve is client A sends me some information, and as a WebSocket, I want to distribute it to client B. So I'm not going to do a ping pong or send it back to client A. So it's better to make sure that I know all the connection to my WebSocket and distribute them to the kind of a router. So for this very simple way, ensure that it's thread safe, of course, and put an ID with an atomic integer and put just a name. So what I did is just I put a name and a value here. And I'm using the Ktor object called default WebSocket session. That's it for the setup. Now it's Ktor. What we are going to do is install the WebSocket. This is from the manual. We say the ping period, the timeout, the max frame size, the masking, everything is by default. But also I'm adding the content converter because I want to serialize and deserialize my WS packet and not transfer just plain text. Then create a pool of connections. And in Ktor, for those that are familiar, there is this routing DSL, and let's create a WebSocket with /connect. So when someone goes inside, I'm just going to register this connection, and then directly I do the try and with the finally make sure that you remove the connection at the bottom. And then you have many ways to do it in Kotlin. I put the more simple way to understand that, just basically while true. And then when I receive, I deserialize them, and then I'm doing something. What is something here? For very basic one, I'm just going from the connection, make sure that I'm not going to send to the one that actually sent it to me to relay it, and then send the data. That's it. So that's it for the signaling server. And the two things that happen here is that we don't send any data to the other one, and we're going to cheat a bit here because, as you can see, I send directly the data. I'm not processing the WS packet because I want to put that very simple for now. This is the moment where you are all afraid, but don't worry. What I said before is WebRTC was designed for web browser, and I'm not a web engineer, but actually, since there is standards and everything is inside browsers, it's actually very easy to create index.html with a bit of JavaScript to actually create a client, client A and client B, using my WebSocket, my signaling server. So what I did, there is my local video, my remote video, a start call button, my URL, with my /connect, and then the peer connection, the remote connection, the local stream. As easy as it is. Then we just wait for handle offer, handle answer, handle ICE candidate, and then depending on the WebSocket, what I can do is set up the media device. It's perfect. Everything is inside the browser, and since it has been around quite a few years, you have every user are going to have a navigator that works with this implementation. And then you use the ICE candidate and you put the element for the view. Same for handle. You see it's very simple code actually, and the remote one, sorry. So what I'm going to display now is we're going to start the signaling server that I just showed you. And I split a bit. What I will do is I will create one page with the local and one page with the remote. So I'm just going to change that in the document. Okay. So this is a Ktor project. We have this section that I showed you. I put some debug. So let's start here. So one thing, I cheated a bit because it's on my network, local network. So everything is on my machine, right? If I wanted to go on an extra network, it requires more job, of course, with the TUN server and with the STUN server as well to discover the IP address. But everything is handled directly inside the web standard. So actually, it's just setting default value, and you can point to the Google STUN server, and then that's fine. Okay, let's go. So I put right here. It's just with the remote, and the left is just with the local here. So you will see how it works. So let me open. And you're going to see that. Okay, so this is me, and this is another So this is the remote. So what you're going to see is like, okay, is it two camera? So no, it's not two camera. It's two different streams, and since it's a local network here. You might be like, oh, it's just rendering this camera. No, actually, since it's inside my network, it's using the nice connection. But if you look deeper, you will see that on the left, on the right, sorry, the encoding not as perfect as here, because here is using my front camera, so full resolution, because it's how it does with the local web browser. On the remote side, it transfers through the peer connection between the two tabs. So if you look deeper, you will see some difference. Anyway, you can see the latency is perfect because, of course, it's on my network, but it's a peer connection. So even if this tab is in South Africa, it's going to work very well as well. Because it's a peer connection. So as soon as I have good network in South Africa, for example, then it's going to be fine. So it was as easy as this, setting up the signaling server, and as you've seen, there was some exchange here. So I received the ICE candidates at some point and sending some frame. And now, since I was speaking, it's the ping, sorry. But you see the candidate, the exchange, everything, the offer has been here. So everything was exchanged and routed directly to the other component. All right. Let's start the presentation. That was the demo. So, Android now. Now that we have our signaling server, let's have a look on how to use it in Android, because I spoke about mobile app. You have probably heard of third parties SDK allowing you to easily set up a video conferencing. This page is getstream.io if you are familiar with. There is LiveKit as well, so they wrap everything. Be sure that LiveKit is actively maintaining WebRTC SDK for Android. So as Android developers, we could directly use the WebRTC, so it's called libWebRTC or this fork from LiveKit if you want to do it by hand. It is a bit, you have to dig a bit in the documentation if you're using this one directly. All right. Return from the field. After digging with this, you have seen my previous sequence diagram with back and forth, so in synchronous, callbacks, etc. So in a client-server communication architecture, the state machine or asynchronous calls are two different paradigms. And this is the way they manage interaction and workflows. To my opinion, state machine is best suited for scenarios where the workflow is complex. It's a bit complex here, involve multiple states, and require a clear state transition. So during the peer connection, from the peer connection, to the WebRTC and going through the signaling server, sometimes things are evolving in a complex way. So I would recommend you to always think not in asynchronous. I ask for I send an offer, I'm expecting an answer. No, what you should do is, okay, I'm just having a state machine. What happens when I receive an offer? I do that. What happens when I receive an answer? I do that. So it's a bit different, but believe me, it's more scalable and more flexible, especially if you want, or if your project manager want to introduce new features. So for example, we will see that a bit later, but what if the signaling server was injecting some things to your clients? How do you handle that? Well, you can create a new packet and handle this as a new state, for example. So for Android, this is the architecture I will recommend. So you have a WebSocket data structure. It's in charge of communication to the signaling server. It's open, close the connection to the WebSocket. Can be used to maintain also the ping session. We have seen that inside Keto, it's for free. And also, as I said, can be used to inject specific command if you want. Then I will put aside another data source, the WebRTC data source, that's in charge of the peer connection. The peer connection is the object, the main object in the WebRTC SDK. It's in charge of creating, receiving offer, answers, setting up the ICE candidates, negotiating the RTC configuration, the stun, the turn server. From the two data sources, what I would do, I would combine the flow from both data sources, product a state that your app will use. So I put that in a connection repository. You can call that a connection use case if you want. But basically, it's going to challenge the fact, am I paired to someone else? Am I connected just basically to the signaling server? What is my state basically? And this is where all the logic will come. And then, to be used by your UI, you can inject event from the user, like mute this one, or disconnect, or start the call to produce a new connection state, for example, or receive some command from the peer. Okay, let's have a look a bit. I have a bit more time, yeah. Let's have a look on the WebSocket data source. So we use Ktor server for our signaling server. Why not using Ktor client for our client? Basically, it's quite easy to set up. It's just here, install the WebSocket, and again, install the content converter. So what I'm going to do, I receive the messages, my WS packet, which I deserialize. And on start, of course, I'm having this open WebSocket session and make sure that, everything is set up. And then, I can take this one. So the session is here, we can close and send messages, and voila. Also, I put it on purpose WS, but it's better to put WSS as secure if you want to be secure. And then that's it. That's Kotlin. I have a flow, so basically I'm ensuring that session is active, and when it's active, I'm sending my WS packet, and when I receive a flow of WS packet, I consume it as a flow and deserialize it with a timeout if I didn't receive on time. For the WebRTC data source, so again, we need a peer connection, which is the object from the WebRTC standard. In my purpose here, I have a data channel. I was saying that before there was audio, video, and also arbitrary data. So if you want to send data, it's through the data channel. So in our case, we're just going to use video and audio, but if you want, you can put it here. Then ensure that there is a job as well to be sure that you can close it every time. And then that's it. There is the connection state, the ICE candidate state. This is part of the data channel if you want to send arbitrary data. And then we already have some callbacks. And what I'm doing, basically, I'm going to state in, and it's going to be sent directly to my connection repository. This is how to create an offer, the answer, the RTC configuration, that's to make sure that it works outside the local network. And closing, and here I was speaking about the stun server from Google. So the RTC configuration can be the default one, or you can specify the stun, or you can use Twilio stun. We started with Google, it was okay, but we used Twilio and it appears it was a bit faster. And the connection repository, I said that I'm going to combine actually all the states, all the value from the WebSocket and the WebRTC. So what I'm going to do is just I have a state flow. I'm combining my peer connection state, my WebSocket data stream, and actually, depending on my packets, I do some challenge. Here, if I receive some ICE server, then I will set up the ICE server, make sure that I create an RTC configuration, set this configuration, send back the ICE candidate. So it's all the things that was asynchronous, but here we can see easily how to split them. So you can actually split that into different functions, but I put that for the purpose of knowing what to do when we receive this packet, for example. The ICE candidate, the answer, and then also I'm saying that I'm connected at the moment, so for my UI to make sure that it's a loading screen. And actually, it's not big, the feedback, it's just here. And sending the value will be just ICE candidate with the value. I'm just following the standard at the moment, so it's pretty straightforward. So that was for Android, but actually this part, what I've showcased you, works for multi-platform. So everybody knows multi-platform here. You have to have a library that works for multi-platform. And what I showed you actually was part of the great job of Alex Shapirov, because he's doing a lot of things, bringing WebRTC to multi-platform. So since WebRTC is a standard, we can take the iOS SDK as well, because it exists, the Android SDK from the WebRTC Android, for example, and we can adapt them, and even from the JS, actually, we can adapt them inside the multi-platform library. This is what he has been doing, and you can contribute. He is very helpful. I had some issue with iOS, and he fixed that, and also we work together. It's a good guy. There is room for improvement, of course, because it's only Alex working on this at the moment, or debugging tools. But the library, we used it on production, and it works just more than fine. How does it work under the hood? He even used Compose multi-platform. So what he does, he created this expect video with a video track from the standard, the audio track from the standard, and then there is the actual. So in the actual, there is this Android view with the surface view, which is basic Android. And for iOS, he is using HTML video view with the content. And again, it's a part of the binding between iOS and multi-platform. So since it's a DroidCon conference, I wanted to do one thing, is showcase you how to do it on an iPhone. So I'm going to use my iPhone. Up. And there is a sample app. So it's Compose multi-platform with the video that I showcase you. And what I'm going to do, so here it's me on the local one. And I'm going to start a call. And here below, so it's like before I split it. So it's the remote one. And as you've seen, everything works on this iPhone. Okay, so you're a bit far, but there is the sound as well, because we set up the audio track as well. So there is audio, video, and we can start a call, and it works fine, and I can split everything. So Compose multi-platform is great for that as well. Up. Okay, what's next? We have seen that from the history, how is it architecture. We have seen how to do it in web, how to do it in iOS. So that's great, but what is next actually? What we've shown is that the peer connection in a mesh challenge, where there is actually client E, client B, client C. Once I get rid of the signaling server, everybody is in peer connection. As we said, it's not really scalable. So there is another way of doing this. It's the selective forwarding unit. It's basically, if you're on a Google Meet, we're just two in the call, then it's going to work. Once we are more than two, you will see sometimes that there is a glitch because actually switching the way of the architecture behind. And basically, so that was a mesh. So it was a lot of one. And then we have the server here. And what it's actually doing is that the selective forwarding unit, so let's put another one. It's called the SFU. So basically, it's a media server. It's the component that is capable of receiving multiple media streams and then deciding where these media streams should be sent to which participant. And actually, its main use is to supporting group calls or streaming broadcast scenarios to everybody. So SFU, they don't process the media, but rather just route around. As such, they consume a considerably amount of less CPU than their MCU, the multiple conference unit that we have seen before. And their performance relies heavily on the network throughout the client B and client on the server to client C. There is a lot of benefits from using this component. We can bring simulcast. Basically, it involves sending multiple video streams of different qualities. So I noticed that client B has a bad bandwidth. So why not trying to make the audio or the video more compressed so the data will be more easily received. And sometimes that you see the camera of the other participant is a little bit blurry. There is temporal scalability, trying to involve encoding on different frame rates as well. So not only compressing, but different frame rate. We can manipulate the media data directly before it was sent or received. So it's called the insertable streams. It's not used for putting ads. It's just useful for custom processors such as end-to-end encryption, for example, to make sure that the connection is safe, or even adding some effects like the filters on the video, for example. And there is also the protocol converter. So if you want to convert the WebRTC to a streaming, like if you want to have this discussion, also send that live to your Twitch channel or YouTube, for example, there is some connection. So to speak about this WebRTC, we have seen there is GetStream, we have seen that there is LiveKit. So why do we have WebRTC companies? The business has increasingly evolved since the COVID, and the demand for reliable WebRTC companies, as I said before, has skyrocketed. While we use WebRTC to offer a powerful foundation for real-time communication, it has some limitation. We have seen that actually creating a signaling server is not so hard, but who wants to have to deal with this kind of network? So WebRTC company, they stepped in because they can improve the scalability and the performance, because it requires some kind of development. For security reason, we have seen that with the SFU unit. Also for customization and bring a better user experience. For example, when we need to put some filters, we need to put some subtitles, for example. And also to make sure that developers actually easier to set up WebRTC inside the apps. This is a list of the companies that I try to find that are actually building their business on WebRTC. So it's big and there is a lot of money. There is many use cases of WebRTC. There is, as I mentioned, telehealth to give healthcare to people around. There is HR tech, fitness as well, social media. I mentioned gaming, of course. Creating some events with friends or even dating apps. So there is actually a lot of use cases of using real-time communication around the world. So what's next? To sum up, as we look to the future, the integration of AI on machine language technologies in WebRTC is set to kind of revolutionize the user experience. With innovation like real-time language translation or subtitles, you have seen that demo of someone speaking in Portuguese and it's already translated to the other guys in English, for example. Noise suppression, if I'm on a coffee shop, there is a lot of noise, then they can process and remove the noise. Also, video enhancement filters, the possibilities are endless, and this is why also they are putting this effort, this company, to bring more effects inside their solution. All right, so I hope I've shown you today that as a Kotlin engineers, we have the tools, the capabilities to achieve this kind of incredible things across iOS, web, Android, of course, whether even in WebAssembly for the future. And also, we're able, as Kotlin engineers, to do some backend stuff. So our skills today, and this is my conclusion, I think are more relevant than ever in this evolving and it's rapidly evolving landscape. So thanks to you for this talk, and let's continue to push the boundaries of what's possible with WebRTC together. Thanks. Can I take some questions or? What? So,
Developing an application which was connected to the drone cameras that we are flying, and they wanted to stream the videos to the application. And it was another use case of using the analysis because we were working in the analysis case.
I didn't hear the question, sorry.
There was an application. Their idea was that they wanted to develop an application which was connected with the drone cameras.
Mm-hmm. Yeah.
And they wanted, to getting the videos with the very small latency. So they were using the WebRTC, and their solution, after a lot of research, was that they have to use the WebRTC, and it was about, I can tell you, 5 years ago, 5, 6 years ago.
How many cameras?
Two cameras, but they were flying, that they were flying, and it was one of the usages of the WebRTC.
Okay. For 2 cameras, for me, today I've shown you with 2 clients, it's working quite fine. For your control room, maybe there is a kind of SFU unit that we have shown that. So someone that actually kind of be a black box and make sure that it records everything on the side. So maybe the thing is you have multiple camera connected actually to one server. So for that, WebRTC for me is a good choice. Yeah, there is almost no latency. We use that for video gaming. It's perfect. Basically, what we did is we put the game on the cloud. Even if we host the game in Japan, playing in France, no latency. You jump, it jumps right away. So it's a good technology for that. Yes?
Is the repo available?
So the repo from Alex Shapirov, I will definitely suggest this one. If you want, I can put the one for the signaling server, but I showcase all the code. As you have seen, there is not so many lines of code. Yeah. But the one from WebRTC KMP, I would suggest to have a look inside. Yeah. Yes.
Apart the only limitation would be the internet connection.
Yes.
When exchanging videos.
Yes.
How handle poor internet connections? Will it be automatically handled by the RFC, or something that you need to do manually?
So there is some with the ICE server. You will see that the ICE candidates. There is no one ICE candidate that is sent. There is many one. So there is a process of fallback. Okay, this route is not good enough. Let's go to this one. Let's go to this one. That's why if you look here, I put inside. There was a list of. We receive a lot of ICE candidates. So to make sure that okay, this route is not safe anymore. Let's try this one, this one, this one. So this is one of the solutions from the standard. But after, if you don't have network, then it's not working anymore. Yeah. Yeah. Right, but thank you. Yes. Test. Where is the? Is it open? No. Next one, this one? Ah, yeah.
Sorry.
No worries. Hello, welcome to my presentation. Today we will be talking about unlocking the potential of the GraphQL in Android development. And no, I think battery problem. No. Not working. This one is open. What is that? This is the synchronization thing.
The arrows should transition.
Yeah, but in the which one is the? This one is the synchronizer.
The synchronizer.
Ah. Yeah. Oh no. Completely. Ah, okay. Maybe this one, right? Yeah. Okay. Ah. Yes. Yes, I am Kemal Selim Tekin Arslan, Android engineer in Holiday Pirates Group, and we have some markets with the different languages. We provide services with these 10 languages as a localization with the GraphQL. And today is our content. Let's talk about the importance of the efficient network communication, REST API overview, introduction of the GraphQL, challenges with REST, why we adopt the GraphQL, end of the day. Let's start with some questions. How many people only use the REST APIs? Only REST? Yeah, half of the room. How many people used or using maybe combine of the GraphQL? Yeah, 2, 3, good. Maybe other part, this one. I never heard the GraphQL. Maybe afternoon I have a workshop. We can talk more coding part because you know that the limited time in presentation, we just say technical part or some definitions. What is the REST and GraphQL? Yeah, let's begin the importance of the network communications. First, battery life is important for us, and maintain device battery by the minimizing data transmission, boosting the application's energy efficiency. Our more smart devices has no good battery now. You know, scalability is the second one. When network communication is optimized and application can handle larger number of the users, data requests improving its scalability and performance under increased load, and bandwidth optimization, streamlining communication, helping utilizing network bandwidth with a more efficiently, ensuring that the data transfers are efficient and minimizing of the consumption of the unnecessary resourcing. This is the important for us for the next slides. Yes, support for the low connectivity environment. We know that every city supports good connectivity, but underground or other limited connectivity part is as important for some companies or some users. And the last one, the improved user experience. We know that in the recent years, many statistics show that when screens in a app screens load slowly, users tend to uninstall our apps. And we check the Google Play statistics like fast load or slow rendering like that. Yes. Second one is the REST API overview for us. REST and its key concept. First, REST is not too old. Representational state transfer represent an architectural style used in a design in a network applications coined by the Roy Fielding in his doctoral dissertation in 2000, and provides structured approach for building scalable and maintainable services for us. Uniform interface, this is the basic definition. we know that HTTP methods in REST part, this is like a predefined for us, and these URL correspond some methods. We know the traditional things, and when client send a request with specified URL, server handle it and return the JSON for us. These get, post, and put delete methods, the classical predefined methods for us. Yes, stateless communication. REST operates in a stateless manner where every client request must carry all essential details for the server to proceed it. And the server does not retain any client-related information between the requests. Scalability and performance, it is important for the our application scalability for the more users, and REST is a state-free and caching mechanism contribute to improved scalability and performance of the APIs, as a resource can be distributed and cached efficiently for us. And shortly, REST offers several advantages, emphasizing simplicity and adhering well-defined standards. REST ensures seamless compatibility, effortless scalability, efficient caching, and design for the optimal performance. Sounds good. And let's check the GraphQL part. The GraphQL fields the type categorize data into scalars representing atomic values like a string, the object representing the complex structure with the nested fields, enum types define the specific set of the values, and for the flexible data schema. In the GraphQL part, we have some schema. We will touch it next. And GraphQL start by the defining of our schema that describes the type of the data can be accessed and their relationships, serving as a contract between the client and server, outlining available queries and mutations. Yeah, we are using the Apollo GraphQL in Android and iOS part, and we will check the Apollo details for us because it is basically server SDK between our SQL server or data server and our clients. This is the example schema. We leverage Apollo GraphQL. Its toolset fully analyze our schema and its fields. When you install the Apollo SDK, SDK detect all details like objects, scalars, interface in our data part, SQL part, whatever you have the SQL server. And this is my production, and automatically predefined our data results for us. And we can continue to its key concept. GraphQL has a queries. It is important for us because the data transferring data and filtering, sorting, some specifying desired fields like that. And we saw that we have a raw HTTP request basically, but the body has one query. Query say, I need a user ID, normal name, something like that, and response just serve the required things. This is another example from the Apollo sandbox from my production GraphQL queries. This is the all fields definitions, and this allows us to flexibility run various queries in pre-development stage, providing critical insights into our data structure. Also, it is fit to multi-language support with single API. And we can first use the query, run the queries with some specified things, and then check the response before the development in front-end part. Yeah, this is the good example for us. Our client sent one request related with whatever it needs, like a post with related details, company, author. It is just one request, not in the rest. We need, that combined chaining response. First, we need maybe set of ID list, and then chain second request with another results list of objects, list of post. But in GraphQL, we just define any combined things, and GraphQL SDK collects these desired properties for us and serve just related JSON for our response part. We have mutations like a CRUD items in the GraphQL, similar to queries, but this is modified data. They can perform actions like a create, update, and delete data. If we want, we can set some user roles also in our schema, manage who is an administrator, and send a delete request or modify request from the front-end part. Yes, challenge with REST. REST poses distinct challenges, and we tackle this by adapting GraphQL. Overfetching and underfetching. The data is important, and I will show something about the data calculation. We sometimes we use the internet like it is unlimited, but many devices or many people use the Wi-Fi to collect something or download something in App Store statistics also. And this overfetching and underfetching solve with the GraphQL. Specified data they need, eliminating both overfetching and underfetching issues. Client can specify shape and structure of the data and use this result directly. Multiple requests in REST API can require multiple endpoints to fetch various data type and define these multiple endpoint in REST part, like big classes. But GraphQL uses single endpoint for all queries, reducing number of API endpoints and simplifying API architecture and less backend effort to develop before the front-end or mobile team. N+1 query problem. In REST, obtaining related data typically involves multiple requests, causing the N+1 query problem, where one initial request triggers an additional request to retrieve associated data. But GraphQL part, the functions responsible to fetch in backend GraphQL SDK function responsible to fetch data for each field in design and requested in the query, allowing our development to efficiently batch and optimize data retrieval. And data loading. When we request something from the REST part, the endpoint retrieve full data set associated with that endpoint. But in the GraphQL part, client enable specified data, and when some part of the data is a fail, GraphQL serve the half of this data, like this part is a success, this service is a fail, and give some response, and we can draw half of the screen. Versioning, the REST, we know that we have some versioning, REST APIs, version 1, 2, 3, and so on. But GraphQL, we don't have any versioning. Robust type system and versionless schema facilitate smooth API evolution without risk breaking changes, allowing client request data in precise structure they need. Yes, this example, another example with GraphQL part. In REST part, we collect something. It will start again. Without GraphQL, our 3 API call, and we get maybe put some data in the trash, but we need to fetch more data without GraphQL. Our API response, maybe our data class don't need, but network part completely get the JSON in the REST API, and we may match just 2 items. Yes, why we need to adapt? GraphQL was developed by the Facebook in 2012 and was open source 2015. It is fully tested and confident for the use live applications. It scales with the requirement even largest organizations, largely because of the powerful tooling, and it is compatibility with federated architecture. And these organizations use the GraphQL, but we know that maybe our structure, your company structure or project structure is not required day one. You just need to check like a new SDK. We need to test this SDK is ready to use or solve my problems like that. Front-end control over data, this is so important. My old experience, old companies, we always waiting to backend team because you know that the product team requests something, new feature, and backend team need a time, and in that time we just mock something in the mobile or front-end part, and this mock or this development process recycle again and again. And in that case, GraphQL part, we just know the data in the database, and GraphQL SDK serve what I need in the mobile site, what I need the front-end website, the big screen or small screen like that. Real-time capabilities, also GraphQL support real-time updates through subscriptions, enable dynamic and interactive user experience for us. Federated architecture, we touch here. And versioning and evolution, GraphQL provides backward compatible approach to schema changes, enable smooth versioning, evolution of the API without breaking changes. Yeah, single endpoint, multiple source. This is the small iconography for the GraphQL client and sources. Single query retrieve multiple sources. This source part is our AWS or something like that, some data sources, and we install the GraphQL SDK between source and our clients, and clients request everything from this part. Also, parallel data loading is important on the GraphQL part. Performance and fetching related data concurrently. We touched at the multiple items, different items from the different sources in the one query, because we know that the user credentials or user details profiles is one data in a store, one our storage, another requested thing in another our data sources, and our SDK requests whatever we want. This is the resolver functions in GraphQL part, fetch all things and serve the results. Yes, strongly typed schema. This clarify help developers understand query and API efficiently, reducing number of errors during the development, because we don't need to wait some API documentation from the other teams when we install the SDK and configure it in the backend part. Then we strongly type schema in the GraphQL Apollo SDK part. Elevating developer experience, efficient development workflow, self-documentation in API side, collaboration and front-end independence, and our current front-end team use the many items, but in the mobile side we just use the less items, and in that case we save something. Yeah, this is the small example. One data result, left-hand side, I just used the 3 item of the JSON results, but the next step, our backend team or front-end team requests new fields, gender, status, blah, blah. And these 5 items maybe is not much more data we first thought, because in mobile part, we just say it is JSON result, okay, continue to parse, map, something like that. But I don't want to use in my UI part, these new items, new fields. And our JSON result just 2 kilobytes increased after this implementation for my front-end or my other teams. And then when we calculate the every not small companies, but middle companies has active users 1 million, and for my company, I calculated the first month of this year, just 2 kilobytes per session. This is the REST API result, and when we calculate the like a 5 times session for the one users, one device, and for the monthly, and 150 million sessions, total number of sessions, and in that case, our network traffic over 300 gigabytes, just 2 kilobytes JSON increased response. And before this, before the GraphQLs, this is the so interesting results for us, and this is the like a who would like to shut down the one AWS server like that and saving something for us. And then thank you. Before the Q&A, I would like to say that this is the more technical topic, and sorry for bothering you, but afternoon we have a workshop. If you would like to develop something with a coding part, install GraphQL SDK, your project, personal project, or I prepared some small project in Android Studio, like a live session. We can develop your project or our samples, and and if you have any question,
So you mentioned that GraphQL is versionless, right?
sorry.
Do we have a microphone?
I don't know. Do we have a microphone more?
So you mentioned that GraphQL is versionless. There's no
Just a second. Okay. Maybe.
Test. So you mentioned that GraphQL is versionless. That there's no there's no breaking changes when you're changing the schema and so on. Can you kind of explain what you mean by that?
Yes. Should I back to schema sample? Yes, this is the like a this is the schema page, and the question is GraphQL is versionless. How can we keep the breaking changes, right?
Yeah. So by your mentioning of it being versionless, it means that there are no breaking changes, right?
The schema file, it is like a STL file. We download it and put the project. It is not has a version, schema version 1, 2 like that. It has some JSON definition completely, and when our data team or backend team add new parameters, if you want to use this parameter, you can just update your schema as a update your JSON definition of this like objects.
Yep.
Blah blah. And in that case, when you don't need, you cannot update your schema. End of the day, your parameters, your object is still in there, and you can go to your query.
Yeah, but if you remove properties or if you change the structure, so let's say a property is on top level and you put it under another object, then you do.
This is you have any objects or scalars and change your data source, data types like that. Your schema know the complete structure. You know, your schema cannot say this must be under this data. Just know our data source has a B, C parameters or fields or objects. When you change completely your object types to interface, okay, you have to update your schema.
Yeah. Yep.
Yeah. And in that case, sometimes we maybe delete or upgrade, but we use the new name, and maybe 3 months later you just delete completely from your data source.
Yeah. Okay.
Okay.
How does this, what's the impact of GraphQL in terms of response time? Like you showed us some queries that we have like nested queries in within another table and inside in another table. Like how is response time filtered?
Yeah, it is too fast because we test like a underground, especially low connectivity, and rest every time failed in the low connection. But GraphQL, maybe you have a just first images and some text. First serve the image to you and SDK handle while your second data source is a fail. It's okay, completely fail. But otherwise, maybe you can put to 10 seconds while using our users use this same page, and your SDK completely push second part of your data to you and draw or trigger your UI automatically your data source. And also REST part, you know that the chaining we used every time, and chaining is a more loading and loading the first one, second one. Yeah, we improve the old way completely. Page has a one loading. It is bad things, but like a skeleton, you know, the each part of the card independent loader, but it is also not good for the rest. We are waiting 3 or 4 seconds for the some combination of things, but GraphQL part is so fast.
Yeah, I'm curious. How do you transition an entire project from REST to GraphQL? Do you do it gradually or as a one block? Or, and especially how do you convince the entire organization, the entire project that GraphQL is the way to go? Do
Yeah.
you have to advocate for it or does the decision come from a higher position? Somehow you want to
In my experience, I think technical part need to fit this migration, because you know that some backend team don't want to migrate something like our development process or time is a decrease after GraphQL. What is next for us in backend team? But in real life, it's not these kind of things. And first, the backend team installed this SDK for the read data source. After that, maybe like a spike task, you can check this data source. First step is okay, we automatically check our fields, automatically API documentation for us, and read the documentation, this page. You can directly run the queries this page without any other developments in the front-end part. And in that case, also you can explain the when use the GraphQL, we for the new things, maybe new parameters. Okay, you need a development, you need a backend team part, you need a new services or new items, but otherwise you don't need any other effort from dependency, other teams. And you can continue your sprint or your life with change or add more data inside your screen and so on. Also, the performance part, many results in the internet. You can check some performance test results, something like that. Also, coding part, you know that REST, when you want to match something, you need to define more parameter, maybe more data classes like that. But in other times, you get rid of some boilerplate code, something like that. If you have time, we can check the workshop sample. Please.
In your experience, were you able to continue to use like strong type data classes, like without having global everywhere, using GraphQL, and also without polluting your views too much with the code? Were you able to do so?
Yeah, you mean that you don't want to add much more data classes?
Imagine on the client, on the front end, whatever it is,
Mm-hmm.
Angular or Kotlin or whatever.
Yeah.
I want to have a way, because I don't know, of using GraphQL but not putting everything as nullable, because in my query, everything can be null or not, right? So
Yeah.
how do you do that without having a whole loop right into the client face almost, right?
Yeah, our experience say everything is nullable because you know that some fail response or some teammates put some null things in there for the maybe one purpose. I don't know, not empty string, completely delete or null these items, these fields inside your data, and in that case, my client continue to live because my query say it can be nullable. It's okay. Another field is a field by the SDK, and I can continue to my life.
Okay, so you use the nullable on everything, right?
Yeah, nearly everything. I don't remember full of structure, but yeah, almost nullable is good.
I think it's kind of like a follow-up question. If a subquery fails, does the whole query fail?
No, yeah, just activate part of data serving is enabled like that, and when we send a one query and yeah one server fail and we don't have any related data, just basic data served to you and also exception served to you. Blah blah. This data sources failed because I cannot reach the X fields like that. And in that case, I can continue to serve and maybe refresh the page, say something to users. Okay, I think that's all. Thank you so much for joining. Have a good day. Have a good break.
Yeah? Okay. That's good because maybe a bit long. So if it's okay with you guys, we can start a bit earlier. So yeah, let's kick it off. I have like maybe 40 plus slides that we'll try to go through. Let's see if we succeed. So yeah, hello and welcome to this talk where I will present about Parch, Volvo's take on composable architecture. Maybe you have heard MVP, MVI, MVVM, UDF, now Parch, yet another Android presentation architecture. Do we need another architecture? Let's see if by the end of this talk I can answer that question. But yeah, let's start with some introductions first. Who am I? Juan Cheradia. I come from Argentina. I've been living in Sweden for the last 10 years. I moved to Sweden because I love surfing, of course. But lucky for me, Lisbon has a DroidCon where I can come. I've been working as a software engineer for more than 20 years now. And since 2010, I've been focusing my career on Android applications, particularly. I've been working for Volvo the last 6 years, where currently my role is a staff engineer behind the mobile core of the app. But yeah, enough about me. You didn't came here for me. You came here to learn about Parch, what is Parch, and how can that help you building better apps, hopefully. Or that's the bet, at least. But before jumping into Parch, let's take a step backwards and talk about architecture in general. Nowadays, it's quite common for an Android architecture or a mobile architecture to follow a simple 3-layer clean architecture, where we have a presentation layer and a domain layer, both dependent on the domain layer. Presentation and a data layer, both dependent on a domain layer that is agnostic towards both of them. Where the presentation consumes our domain values to show a UI on the screen, the data will provide the specific implementations for our domain definitions, and it will provide access to database, to the cloud, and through the cloud, it will provide access to the real world. So let's try to zoom in on our domain layer. Before that, let's talk about application state. Every application has a state that will tell you what you will end up presenting on a UI, how you will end up reacting to different behavior, different events. Wrong door. And this state is implicit of what is happening on the memory on the device that our app is running. Okay, sorry for that. That, of course, has to happen. Okay, let's see if we can come out from that. Okay, where were we? Let's see when we will get disturbed again. We needed some icebreaker, right? So we were talking about the domain layer. We were talking about application state, how the object instances that live in the memory will define the application state. Why is this application state important? Those objects, the values that they keep, they will have their own life cycle. They will change from different events. And as a reaction of those changes, our UI or how our app behaves will change. I'm pretty sure that you have faced a bug report that feels random, that is hard to reproduce. Or whenever you are building a new feature, you want to test that feature, you want to bring your app to a certain state, right? That's why the more control we have on that state, the easier that will make our life as a developer. All this to say that immutability on entities is good, that we, from our domain, we will expose immutable entities, and those immutable entities will be the input for our UI to be present. But immutability on its own is a bit boring, in the sense that there wouldn't be life without change. We want our app to be able to change the state. We want to react to the real world changes and represent it on the app. We want to react to user interactions. How do we do that? We do it through use cases that will act on the immutable entities, create new entities, new immutable entities, and publish them for our UI to update. Okay, that's a bit of a brief of a high-level architecture, clean architecture. More likely nothing new here. How does Parch fit on this? Parch will help us to structure the presentation layer. It doesn't really bring new concept. Mostly it's a cherry pick of all the different architectures, as I mentioned before, MVP, MVVM, MVI, and adopting what it makes sense for us, dropping what it doesn't make sense for us, and with a strong sense of single responsibility and focusing on the single responsibility principle. So in between the main components of Parch, we have the Compose UI that is in charge of drawing a representation of a world in a canvas. The canvas will be the user screen. This representation of the world will be given to the Compose UI by our view data. And this representation of the world will be created from composing or combining, mapping all the different, and there we go again. This will not be good. I'm scared of resenting. Fuck. Okay. Good thing that I started earlier. So the view data will be combining the entity, the domain entities, into the values that are needed for the Compose UI to be drawn on the canvas. But then we have the interactions that the user does, and our Compose UI already have its single responsibility. We don't want to pollute our Compose UI with an extra responsibility. And that's where what we call orchestrator comes into play. All the interactions that the UI will receive will be forward to the orchestrator. The orchestrator on its own can decide if the interaction is a navigation or if it's a use case that has to be triggered. The orchestrator doesn't know how to play the instruments. The musician here are the use cases or the navigation, but the orchestrator decides when each of the things has to happen. Now we have a brief understanding of the relationships on the different components, but what does it mean in practice? Can we be more specific about these components? Let's see a common data flow and how that is solved within this architecture. First, let me showcase a bit of the app. We are showing a snapshot of the car status. We want to show as much as possible the real time of the status of the car, if you open the door or close it. We want to show an overview if your climate is running, if the charge is running, if you forgot it unlocked or not. So how our UI will get updated by this? We say already that the Compose UI is the one in charge of drawing on the screen. This Compose UI depends on the view data to get the UI values. And the view data on its own can depend on the car status flow, Kotlin flow, that will publish immutable entities. That means that the data flow is actually the other way around, right? So whenever our real car updates the status without getting into what happened in between there, going to the cloud to the data layer, reaching the domain layer will publish a new car status. This car status will be observed by the view data and be transformed into the UI values that are needed. These UI values will trigger a recomposition on the Compose UI, updating what the user sees on the screen. It's quite straightforward, quite linear so far, right? Does this relate to what we see on the code base? So far, we focus on the log portion of the screen. Let's see how we can code that part in. So we start with the Compose UI, where we define our role. We want to show the icon that represents our log's status. This icon is calculated by the view data. And we are collecting as a state, relying on the composable features from Jetpack Compose to trigger recomposition whenever it changes. And this will happen every 5 minutes, sorry. Because, yep. I'm scared of restarting because if I restart now, it will take up to 40 minutes. Okay, so the log status icon comes from the view data. Next to it, come on. Maybe we can do that. Yeah, because it will be every 5 minutes this, and I already destroyed the video and the live presentation. Yeah.
Can you drop whatever you have?
Let me see. AirDrop.
Like a PowerPoint page.
It's which one is yours? Okay, we are back. Thank you. Sorry for the people online. Hopefully you are still there. So we were checking how do we react to changes. We saw this part already. So the compose UI is depending on view data values that are calculated from our car status flow. Whenever a real world event happens, we will publish a new status immutable, it will be converted into UI values, and then it will be recomposed. As I mentioned, this is quite straightforward, quite linear. Let's see if that relates to the code base. We will start with a row. On the row, we have a log icon that will come from the view data, and we support ourselves with collector state. The same will happen when we want to show the status text. As well, we come from the view data, and it will recompose whenever a value changes there. I will skip the compose UI test because we won't have time. But let's see how do we go and test the view data with this approach. Before that, we should write the code of the view data. But yes, so this is the code of the view data. As well, it's quite straightforward. What's the view data does? It exposes, it reads the domain. It exposes two values for our UI to consume, and those values are calculated from mapping the published immutable entity. We can, if we like, rewrite this on a more single responsibility way by following extension functions, but the complexity is the same and the code is still the same. So we have pretty straightforward mapping here. We can go and check how it relates on the test. For testing this, we will need our test subset that we create on every setup to make sure that we are testing a new subset. We will fake our dependencies, the domain logs flow. You could use your favorite mocking library for this. Spoiler alert, if you use a mocking library, it will take twice or more the test to run. If it's simple enough, I recommend fake it, but Mockito or Mock-K are powerful as well. And if we want to test how the text ID is created and if we are publishing the right values, it's as simple as that. We inject a new value into our fake domain flow, and we verify that the expected value is the one that is published by the view data. For this, we are supporting ourselves into JUnify capabilities, which are parameterized tests. This one will give us the control values for our test that are the ones that we are comparing against each other. Then we have a test for the text ID. We can write pretty much the same for the icon. And then we would like to test as well that whenever a view data is created, we are consuming the right log status for the right VIN. What is a VIN? Vehicle identification number. That's a general thing for every car. So that's how we are going to tell this is the car that I want to listen the status from. So to recap this part, whenever our car publishes or changes the status on the real world, our domain will publish a new immutable value that our view data will convert into UI values that eventually will trigger the recomposition, and our UI will get updated. But that's about the data flow, one direction. We want as well to be able to interact with the app and to be able to force changes. So imagine that you forgot your car unlocked. Instead of running to the car and lock it yourself, because your app, the app is telling you your car is unlocked, you can just open the locks screen and trigger a remote lock that will lock your car. So how does that go into the app code base? Let's start with the navigation. We know that the compose creates the screen. Whenever we click on it, the compose will forward that click to our orchestrator. Our orchestrator in this case has a responsibility of deciding what to do with that click, right? And here what the orchestrator will understand is, as a reaction of this click, I need to tell the navigation to navigate to a new screen. The navigation eventually will trigger a recomposition. Spoiler alert, here we are using compose navigation under the hood to update our UI and show the new screen that the user should be there. On code base, as well, is not rocket science. We would need to alter our row, so we add the clickable modifier, and we just forward the on click to our orchestrator. Of course, because of that, we need the orchestrator as a dependency of our UI. And the code on our orchestrator, again, is pretty simple. We have a single dependency on the navigation, and the orchestrator tells the navigation where to go as a reaction of the click. Here we could add analytics as well. We could add any other observability metrics or extra logic that is not given by the navigation. If we want to test the orchestrator, as well, it will be quite straightforward. We create our subset of tests, the orchestrator. We fake and set up our navigation. And then we test that whenever a click happens on a VIN number, we are navigating to the right screen with the right parameters. As well, using parameterized tests. It's always good to test with at least 2 or 3 values. Try to, if you have corner cases, try to use the corner values as well. In this case, beans are just strings, so they have a specific format, but we don't care of those here. Yeah, so navigation was easy enough. What about locking the car? What about triggering a use case? The part of a click, we are on the same. But here, the orchestrator will invoke a use case. The use case, through our data layer, will start triggering a set of different logics, calling our backend, sending an invocation to our backend. The backend will send the lock invocation to the car. The car will try to lock itself. But meanwhile, all this happens, we want to give some feedback to the user. So we can have the client logic that while we are waiting there, we can publish a new car status that says locking. The view data will understand that car status and publish the state, the UI state to the UI for it to give the feedback to the user. Eventually, the car will lock. The backend will notify the app. A new car status, immutable car status, will be published by the domain. That will be understood by the view data, as in, let's convert it to a locked screen and a locked UI states. And then that will retrigger the recomposition to update our screen into locked. If we go to the code base, we don't pay much attention to the UI here. We care about the connection in between the UI and the orchestrator. Again, it's straightforward. Every event that we want to trigger from the UI, it will go directly to the orchestrator. The UI shouldn't do any logic on it. The orchestrator is the one that will decide what to do. And then the orchestrator will define that interface to be able to attend those events. I don't know if any of you has implemented MVI before, but model view intent, the intent part of it defines the different events that the UI can trigger, right? Those events usually on MVI are defined as a data type or a enum, a seal class, a seal interface, whatever flavor you prefer. Instead of those events, in Parch, there is a correlation to the public API that the orchestrator is enabling to the UI. Instead of having an enum that says log click event and unlog click event, that is published through the public API of the orchestrator. But the motivations are the same in both cases. Our orchestrator here is triggering the use cases. And then again, the test for it is quite straightforward. Whenever a click happens, we verify that the use case was triggered on the right way. So if we make it slightly generic, we can say that this is a reactive architecture where the Compose UI, whenever the Compose UI has an event, it will forward it directly to the orchestrator. The orchestrator will decide what to do with the event, more likely end up invoking a use case that will trigger some process on our data layer, eventually creating a new immutable data entity that will be captured by whoever is observing on it. Maybe one view data, it may be many view data. That view data will convert it into the view state that our Compose needs, and then the Compose UI will trigger recomposition. If you have been in Android documentation, official documentation not so long ago, you may have seen the UDF, unidirectional data flow, where the state flows one way, event flows the other. I hope that you can see the equivalence in the previous event that I showed there. So yeah, hopefully you have a better understanding on the different components, how they relate to each other, how they handle data and events. But we talk about composition as well. We have two levels of composition. One is given by a composable on its own, Jetpack-Compose, where we have different composable functions that can be attached to different components on the screen. Each of these composable functions internally can have their own representations. But here we are talking always about pure UI representation. We are not having any extra logic, right? We want with Parch to bring this composition to the next level. The next level for us is a smart component. It's not just splitting in UI, but if we take this screen, for example, to show in the top view, reacting to open doors, closed doors, or all the images there, we will need to be listening to the car status, convert that car status into these images, and then trigger the recomposition. On the top, we could be listening to a different entity, car information, and then map that information to year and model and show it on the screen. We could be listening to a car location, triggering a geolocation API and show the address where your car is parked with the weather of it. The same for the battery level. If we have a message inbox for in-app messages, we want the logic of do we have unread messages or not. And for example, here, this part, we saw it a bit. We have what we call remote functions sidebar or remote overview sidebar. That each of its own, even when they are simple enough, if we put all together, they will get overly complex. And then if we try to map everything on a single UI here, we will start having these issues of app state that changes randomly, right? It's because we designed it to change it randomly. So how we go on it? Each of these components, we can build it as a smart component. And then our UI is as plain as this, where we have a header that only receives the VIN number of the car. Then that component will do all the logic internally. Subheader, battery status, message bell, and we can focus on the control sidebar, right? This remote control sidebar right now has 3 smart components on its own. One of them is the one that we already built. We built the central logs overview UI, but there is a small mismatch here. We are sending a VIN as the argument, while what we built is needing a view data and an orchestrator. So how we map both together? On its own, the view data needs to get the flow from the domain. The orchestrator needs to get the navigation as well. So we have the helper function part that will help us put everything together. And the other thing that you may have seen is the use of dependency injection. We are relying on Coin. It's a service locator framework to solve the problem of dependency injection. But easily this can be rewritten to use HILT. And then Coin will make sure to create the right view data and the right orchestrator to pass to our central logs overview UI. Okay, let's zoom in even more. For Coin to work, we will require to create a scope and define the different factories of our components. In HILT, you do that through annotation. With Coin, you could do it with annotation as well. We find it a bit more explicit and easy to follow, easy to onboard people by being explicit on it. It's not a lot of code that you need to write. It's not code that you need to test neither. So it's a little effort for big gain, on our opinion. Then Coin will know how to create this following those factories. That factory on its own will know that needs to get navigation as well, already existing on the dependency injection layer. On this sense, in Coin, we will define the different factories for every UI component that we have. We will also define the different factories for our domain, or the implementations of our domain. Now let's zoom in into Parch Composable. The first thing that we do is to write down the content. This is like any other composable function. But then for Coin to find those factories, it needs a scope. We need to create a scope, and we need to provide it to the composition contest. I don't know if you have used yet composition local, but it's a way of provide extra context to your compositions. On this case, we are providing the coin scope to be used for our content that is the central logs view UI. So whenever we execute the central logs overview UI and coin inject try to find a factory, it knows what scope to create and go and get the factory from there. You may notice that when we created the scope, we are passing an argument there. That argument is to identify which of all the scopes that are defined in coin we need to create. And of course, is extra. And we go all the way. It's an extra argument of our composable helper function. Last step that we require here is that whenever we exit the composition, in order to avoid leaks in memory, in order to let all the objects be garbage collected, well, first we need to map it to the parent scope in order to get the navigation. The navigation will be on activity level. Coin has a stack of scopes, nested scopes, and the navigation will be exposed through the activity. And then we need to clear or close the scope whenever we leave the composition, so we are not leaking any memory, any object. Main activity. We have a single activity and no fragments, no nothing, pure UI, composed UIs. The main activity, main responsibility is to declare the navigation and handle the big navigation. We are using composed navigation, and we will be creating the app content there by providing a scope. On this line, declare navigation, we are injecting the navigation into the coin scope. So it's available for every part composable later. Our navigation is a simple interface. Navigate to, and it receives a UI. Any UI identifier can be passed to the navigation. And then under the hood, we have an implementation that depends on the nav host controller. As well, quite simple implementation. We added special cases for navigate back and quitting the app. And it's declared on the coin scope on the previous line, as we saw before. Then we have this app content that is defining the navigation graph. In this navigation graph, we are defining all the different UIs that will be a full screen of our app. We can also define if we have a button sheet or not, or a modal, we can define it here. So whenever our orchestrator says navigate to a new central logs UI for this bin, that will be mapped to our navigation graph and trigger the right composed UI that was defined before with its own injected view data and its own injected orchestrator. So for a full recap, we have a main activity that exposes the navigation. Through the navigation graph, we define the different screens where the app can land. Each of these screens on its own can be multiple parch components, where each of these parch components has their own complexity, right? And we are putting everything together thanks to dependency injection and through coin. Final words. Only 5 minutes ahead. Well, simplicity is the ultimate sophistication. I'm pretty sure that you weren't amazed by the code base that I showed. Everything was quite straightforward, hopefully. But you can solve complex problems by composing simple solutions or simple blocks, right? Myself, I believe that if a solution is complex, it's because you may be misunderstanding something, either from the problem. And whenever I find myself with a really complex solution, I stop, do a step backwards, and I ask myself, what am I missing here? Because software doesn't have to be complex. The sum of everything maybe is complex, but individual solutions are pretty much straightforward. Software architecture is about clear responsibilities and boundaries. As I mentioned before, Parch, MVP, MVM, MVI, they are different flavors of splitting responsibilities on a similar way. The rest is mostly code style, how you feel comfortable with. In the whole code base, I'm pretty sure if you pay attention enough, you didn't see any superclass that we were forcing our components to be part of. You didn't see any, other than the declaration of the UI identifier, the rest it doesn't have any restrictions. That can be good and bad, depending on how mature your team is, because with the freedom comes responsibility. But we take it as a good thing. We have minimal dependency toward three parties libraries, and only under the hood. We are not exposing those dependencies to the whole app. If we want to change coin to hilt, we do it only on the dependency injection layer, and all our UI code, all our view data, all our orchestrators, we don't need to touch a thing over there. If we want to change navigation compose for the next great navigation library, we do it only on the implementation of our navigation abstraction. The rest of the code will be untouched. Dependency injection is key. Not much to add there. And then let's see if any of you guess what Parch stands for.
Presentation, adapter, repository, was the C, and then
You started good, but then bien. Bien. Yeah, sorry, the Spanish came out from me. So yes, presentation architecture. We had that same problem. Parch is actually an evolution of other architectures that we had. And with that evolution, we changed the names of key players. We had something that was a presenter that now is not a presenter anymore, and we changed it to something else. And then we say, why bother ourselves with these acronyms? Any of them will be a presentation architecture. Then we have the flexibility to change the names as we like without bothering about the high name of the architecture. And with this and all the accidents, we are done. Thank you for staying. I don't know if we have time for questions, but yes.
So I noticed that you didn't use any view model.
Yes.
And I know that it's not necessarily required to use view model in Parch architecture.
Yes.
And I noticed that you are controlling your scopes by creating the local scopes. But is there any reason that you didn't use view model in Parch?
You could use it you can put the view model as well on your dependency injection layer. It all depends on your needs.
Okay. Okay. I hope everyone can hear me. Yes. Okay. I'm Kinara. We're going to talk about Android and Arduino. I came across it pretty randomly, so I think of it as a love connection. A little bit about me. Yeah, that's not working. A little bit about me. I studied to be an electrical engineer, so I still have a little bit of love left over for electronics. And I've been doing Android for about 6 years now. Yeah, I have a 3D printer of my own, so this construction here is entirely 3D printed and completely modular. And so I thought, what can I do with this that all mixes my love of electronics with a love for Android? And so this talk is going to be introductory. It's going to be about how we can connect Android to an Arduino, what we can do with it that's beyond what sort of normal electronics can do in an easier way, at least. So yeah, okay. So first thing we'll talk about why the tentacles. I'm sure a bunch of you are wondering what is wrong with me. So that's the first thing we'll talk about. The second thing is how to connect a USB device with Android. It doesn't have to be Arduino, it can be something else. It can be a USB accessory, another USB device. We can do a lot with all of them. Number 3, we'll talk about a little bit about the construction, the design process, and how I went through with designing and printing this. And then in the end, we're going to talk about the most important part, which is sending input from Android to the Arduino and then back. So from sensors back to Android, and then from Android to the Arduino. All right. First, why the tentacles? 2 years ago, I came across this really interesting robotics article that talked about how tentacle movements work in nature, right? Think of a constant length of string. We have an equal length on both sides. If we reduce one side, length on one side of the string, the other side increases, right? This is how it works. So we have the resistance to the longitudinal compression, and then we have an extension on the other side, which is how it works. This is how we form a C, right? If we wanted an S, we would need 2 of these. We would form one C and then another C, and then we get an S. So I was looking at this paper, which is really interesting, but I won't go too much into it. What it says is that we have a universal joint, right? So it's a linear guide, and then we have a spacer disc, and then we're giving those springs as tension. We're making sure it doesn't just flop around. We're giving it the tension to maintain its shape. And then, like I said, the first section, this can form a C, and then the second section can form another C, which makes us form multiple different shapes with this thing. Okay, so there was also another experiment that I read about. It's an open source robot that was created for surgical robotics research, and it was really interesting because this was 3 segmented, which means we can make a complete circle with this. And so with the kind of tension and pressure and all of the things that we do with this, we can do a lot of different things, and this is actual research, right? And so I thought, how can I make this easy? Something that I can make and something that relates to the things I know. All right, so we have segments, and then we have the servos that move these, right? So it's focusing on simplicity. And then once I read that, I thought, how can I do Android, and why Android? Number 1, when we're doing electronics, for the most part, we're using buttons or potentiometers to change whatever values we need to have custom values inside this. It's not just a binary on and off, right? Number 2, ease of debugging. With Android, you can see exactly where it went wrong, right? You can not just debug the Arduino, but also the input that you're providing from the user. Number 3, customization. Just imagine it, like, you know, when you have lights in your room and then you can change all the colors with Android apps. What if you could do this with complex electronics projects? You can make a UI that helps you change every single thing about the project. That just provides a wide range of opportunity. Then the first thing we'll talk about is how to connect a USB device with Android. It doesn't just apply to an Arduino, like I said, but we will look at it from the focus of an Arduino. Okay, the first thing we're going to do is add the user's feature, right? Because not all Android power devices are guaranteed to use a USB host. So we have to include this to make sure that our application uses this library. And then we want our application to be notified every time a USB device is connected, right? We don't want to open it and then say, oh, maybe I have a USB device. You want to make sure that you have a USB device. So what this action here does, include with the metadata, is to look at the device filter, see if any of these particular devices are connected to our Android, and then open the app if we do. So in the USB device filter, what do we have? We have an XML file that we open in our XML resource directory, and then we mention vendor ID. You can also mention product ID, a class, a subclass, a protocol, pretty much a wide range of things. Or you don't need to mention anything at all, and then you can see what you have, right? Okay. Next, what are we going to do? We are going to initialize a USB manager. This is the manager that we retrieve from the system service. We're not really creating it. And then we're going to get the USB device we need. So our manager provides all the devices that are connected to your USB port, right? And then we're going to get it. It's a very big object. It has all of the information you need. But here, the vendor ID for Arduino, the standard version at least, is 9025. So that's what we're going to look at. If you have any cheaper versions of it, you might want to look at what vendor ID it has. Okay, so we have our USB manager and we have the device. So now we're going to request USB permission. Of course, if you give a wide range of USB permissions already, you don't need to do this. But always a good thing to request user permission, especially now with Android, so I would recommend it. Next thing we're going to do is find the interface. Most USB devices have multiple interfaces, and you can use any of them. It's just basically a pathway for your device your host to connect with the device. So here, let's say we pick 0, right? And then we have to figure out which one is the in endpoint and which one's the out endpoint. Here we're assuming 0 and 1, but we shouldn't be assuming, right? We should be able to find out which endpoint is the input endpoint and which endpoint is the output endpoint. How do we do this? With Android, it becomes really easy because we're just going to iterate through all the endpoints, and then we know we want to transfer data. So we're going to look at the type that is the transfer endpoint, right? And then we also get the direction. So if it's an in direction that we're looking at, we're going to say, okay, this is an in endpoint, an out endpoint. And so we're going to save this, much better than guessing what it's going to do, right? So in case of bulk transfer, we need this because especially when we have input coming in from the Arduino, a byte buffer is going to be filled in, and then we're going to keep resetting the byte buffer. So this means that we need a continuous stream of data. We want a large transfer here. Yeah, so we have a bunch of USB constants, again, for a bunch of different things. You can always look into it. But this is the simplest part of it. Okay, so we have our in endpoints, out endpoints. We have a manager. We have our device. We're going to connect the device to the USB now. Okay, so now with the manager, we're going to open the device and then claim an interface that we talked about earlier. So this interface has the endpoints that we need to send the data to and from Android. Okay. Next part, this is interesting, a little complicated, but interesting, because first we need to reset this interface pathway, right? So we're going to say, we need to give it specific parameters to reset it. And there are a bunch of things. This is Java, which is why they're all commented out. But what does 0x21, 0x22, what does this mean? This is all hexadecimal, right? And the interesting part about this is that you don't need to wonder what it means. It has 3 specific paths, right? The first thing of this is the direction. So we're going from Android to the device. That's the first part of it. The second part of it is telling us that it's a class-specific request, right? And the third part, the one part, is telling us that this is to an interface. So this is a class-specific request directed towards an interface, telling it to reset it, right? So the 0x22, that's the request that we have here. It's basically clearing the control lines, right? So we're making sure that the hardware data flow happens correctly. Okay, the next thing that we do is setting the baud rate, because what does baud rate mean? It's basically how many bits per second are being sent across from our device to the other device, right? We will talk a little more about the baud rate later, but here we are also setting like stop bits, parity, data bits, not things that you really need to worry about usually, but if you have something specific to do, this is where you set it in Android. So you know exactly what you're setting. You don't need to worry about a bunch of different things. Okay, so we have our USB manager, we've reset it. Now we have our connection. We're going to register a receiver, right? Which is pretty similar to how we do usual receiver. This is a broadcast receiver here. That's what the USB is doing. So we're going to add these actions, right? So we are going to add these actions to the intent filter so that it listens to the USB device. So we have the attached one, detached one, and then we register it. Okay, so now in the callback, we're going to use the broadcast receiver to handle these events. And of course, in onDestroy, you have to handle how the connection gets destroyed. Okay, so there are libraries already that are really, really good. The first one is very comprehensive, has a really wide range of devices. I would recommend it if you were looking for something more complicated. The second one is very Arduino weight, very lightweight. You can use this. The reason I mentioned all of the connection is because it's easier to debug when you know what exactly you're doing. It's very, very easy to run into a bunch of errors with Arduino, especially because the connection isn't always stable. There are errors that are very hazy, very vague. So you have no idea what's going wrong until you know what's wrong. Okay, so we've talked about how to make the connection and why the tentacles, even if, yeah, I don't think I need an explanation for that. Okay, so I'm going to talk a little bit about how I went into this. So first, like I mentioned, this is the first paper that I did run into. So it talked about having a disk in between, and then we have the springs which are going to provide the tension so it maintains shape. And we need the universal joint in the center that provides a 360-degree motion, right? But it should not move in the Z direction, only the X and Y's. So how do we do this? First, I created a disk, something on par with that, right? So then it has the 4 holes on the side to run the disks, to have the springs, and then one in the center is a universal joint. So this is how it looks like. You can always look at it later. So there's the universal joint in the center, and then we have, this is one spacer disk set, and we have a bunch of these to make a length. I didn't make it too small because that will look questionable. But this was the first thing that I made. This has no electronics at all. So this was the first iteration of this. We have 2 pulleys. The X pulley makes sure it moves in a C in the X direction. The other one in the Y. So when we put those 2 together, it can move in a 180-degree plane, right? The next iteration that I did was a servo-based one. So it had 2 of these, and then it did this. So it was very cute, but a bit bulky, and I wanted something that was more compact and looked really nice. Okay, so then I thought, okay, I need to make this longer. We talked about a single segment before, so I wanted to make it a double segment because then it can do more complicated, really pretty S motions, right? So for that, we needed 2 servos for the previous one, right? So we needed 4 holes. It runs through one end and then the other end. If I wanted an S, I needed 8. So same thing again. We have a universal joint in the center, and then it goes this way. Okay, so we have a bunch of them, and then now I made it more compact, right? And so I went with a really flat base. We need all of the servos in here, so I said, okay, let me have servo holders that hold it really tight, and then they can be screwed in. And then you add the servos in there, right? And then we have the pulleys that were all printed in, which needed to be printed in 2 parts because we need the space in the center, and a 3D printer is questionable with spaces that print on top. And then we have our screwed in holder, so it can hold the top. And then we have the top on top of that. So it has a spacer disk built in so that the rest of it can be connected directly to the base. Okay, so this was one of the first iterations that I did do. And it worked pretty well, but the pulleys were so small it didn't move much. So I thought, okay, let me make them slightly bigger. And so that's how I ended up with this. That's a lot about how the spacer disk was made, and the springs were actually something that I thought about a lot because I bought a big set of a lot of different springs, and I thought, okay, what would actually make sense? What kind of tension would it need to make sure it retains shape? It shouldn't be too loose, which means that it would just really spring back and forth. If it was too tight, it wouldn't move at all because these servos are really cheap and don't really do very well. So we want to make sure that it had a good amount of thickness. So it took a bit of iteration, and then, yes, so we have the strings running through the pulleys on 4 different sides. So the first 2 do C's in the 180-degree plane, and then the other 2 do C's in the next plane. Okay. So now the really interesting part, which is how do we send in, the data from Arduino to Android and back? We have our connection, we have our devices, we have made sure that they're both connected. Now, how do we send the data? Okay, before we do something really complicated, we will start off with a very simple LED example. Let's say we just want it to blink, right? I'm not going to show that because I don't have it, but I have the code. The first thing we're going to do is use a byte buffer, right? For let's say 1, it's the command we're going to send to make sure that it blinks. That's an on, right? So we're going to convert it to a byte array and put it into a byte buffer, right? And first thing first, though, we need to send it to the out endpoint. We have a connection, and then we're sending it through to the other side. So we have to make sure that we use the out endpoint that we found earlier, right? We went through and found the direction and the type, and we said, okay, this is the out endpoint. So we have this saved in our activity. And then we're going to use the same thing to use at the out endpoint, right? And then, again, we don't want to run on the main thread. We want to make sure it's on the I/O. We don't want to block the main thread, don't want to freeze anything, which can happen, especially because this is a long-running process and very time-consuming. If you would accidentally run into a loop, you're just stuck, and then you have no idea what's happening. So it's a very good thing to run on the background thread. Okay, so what does this do? The byte buffer here is going to queue the data for us so that we can send it, and then this is compatible with like native USB communication. So that's what this is going to do. That's why we're using a byte buffer in the first place. So any information you have, you will always send it through the byte buffer. Okay, so first we're going to initialize the request, right? And then in the highlighted area, we're going to queue this byte buffer. So we're going to say we'll put it into the queue for the USB device. We don't know if it's done yet. We don't know if it will do it. We're just going to queue it. And then if it didn't, then we can always say it failed to queue, right? So the way that we handle error messages here is really important because it provides us every single step. So once we've queued it, we know that it's queued. Then we're going to wait for it to see if the queue is successful, right? So it waits for the request to complete, the connection.request wait, and then we're going to check that the request we sent is the request it executed, because it might have something else in the queue, right? It could have something else that it is doing from some time past. We don't know. So we're going to check if the command is the correct one we sent, and we say, okay, this has been sent. Now, we're going to check if Arduino will do this. How does it do it? This is where the baud rate comes into the picture, right? So we're going to set up our Arduino. How many people here have worked with an Arduino before? Yes. Okay. So serial on Arduino? Yes? Okay. So to set up a serial, what are we going to do? We're going to send the baud rate to the, we're going to set up a baud rate, right? And then this tells the Arduino to get ready to exchange messages with the serial monitor. In our case, it's going to be the Android, right? So that's 9600 binary ones and zeros, and it's called a baud rate. This is going to be per second. For example, this is normal for an Arduino, but if you're using an Arduino Mega, for example, it has serial ports with different baud rates. It can be 11,960 something. So depending on what kind of device you're using, you might want to check your manual or what kind of baud rate it employs. Okay. So next thing we're going to do is check if the serial has any available data, right? So if it has that data, we're going to read it. Now this read can only read one character at a time, which is good in this case because we have the 1, and then we'll say, okay, if it's a 1, we're going to glow the bulb, and otherwise no, right? So this is perfect. Reading here is always easier than sending. Sending is always going to be the hardest part, no matter if you're sending from an Arduino or the Android. But reading is always easy. Okay, so we have a serial class in an Arduino, which is based on the stream-based class. So what does this have? It's going to check if it's available. It can read, find, read bytes until, and read string until are really, really good because you can't just keep reading one character. I mean, you can with a for loop. Not fun to write for Arduino, but this will be much easier. Stream really defines all of the reading functions in Arduino. So any core functionality that you use that has a read will use this. Like serial, for example, wire or Ethernet, any kind of Wi-Fi, all of them use the stream-based class. So you can always use this no matter which way of communication you're using with the Arduino. Okay, so for the servo, which is what we're using here, we're going to talk about what we do on Android. Now I'm going to do a really simple example, and then I'll show you what I did. Okay, the first thing, just use a normal outline text field in Compose, right? I'm going to have a remember mutable state of for the server angle that I will enter, and then I'm going to send it back in the callback called onMoveServoClick. So let's think of it like this. We'll ignore everything on the top. We just have the outline text field, right, with the servo angle, and then we're going to send it. So what are we doing here? In the callback that we have called onMoveServoClick, first we'll check if it's connected, because we have that information already from when we made the connection and have the device and checked out the endpoints. And we're going to do something similar to what we did with LED blink, right? We took the servo angle, we converted it to a byte array, and then we put it into a byte buffer. So this byte buffer is queued now. We initialize the connection with the same out endpoint, and then we're going to queue it in again with the same byte buffer, wait for the connection, check if the request is the same one that we sent, and so it's sent. Now, we need the Arduino to receive the same servo angle and say, okay, I got the same one. So here we're going to use read string until, which is why I mentioned it. What this is going to do if you send a bigger number like 90, 100, even though this takes only until 180 because it's a servo, we're going to read it, and then we're going to check for what number it is. Of course, the easiest way to move a servo is to just say write, and then it would move in a questionable number of time. You don't know how much, and if it's too much, it will just fly across the room. Do not try it. So that will happen. So what we're going to do is put in a for loop and move it step by step, right? So we're going to give it 15 milliseconds, which is a really small amount of time in the scheme of things. It will move in under a second or two. Okay. So how do we receive data on Android? We've sent it. Actually, before we do that, I will show you how this works. Hopefully it works. Okay. So this is the same app as that one. So I'm not fooling you. And let's see. Does it move? Oh yeah, one of them moves. Two of them move. Can everybody see? Oops. Okay. That one's working much better. Okay. You're always welcome to try it out by yourself. Later, we can do multiple different numbers. It's going to move in different directions. It has all of the U-shape and S-shape capabilities that we were talking about. You can also change which part of it is moving. So you want the bottom to move in a C, the up to turn in an S. They're all going to move in completely different directions. So you can really make sure which part of it is moving. I think the next thing that I would definitely like to do is to see how much of space it can map, in the sense that I move it in different directions and be able to do it in maybe a movement curve, like a color circle, for example, where it goes in different directions and I can just make it go in the space wherever I want, right? Which is possible with Android, because I can just have a Compose drag and drop facility, or I can just have a something with on touch. And so that makes it really easy for me to be able to do this on Android, right? That's the best part of it. Okay. Yeah, it's fine. Okay. Yeah, I think there's some left over. I did not do that. It did it all by itself. Okay. Yeah, you're welcome to try it out after the talk. Next thing we're going to talk about is how to receive data on Android, which is just as cool, right? What if I had a sensor on top of this that moved every time I walked across it? Home decor idea, right? That's the plan. I want to have like 6 big tentacles on the wall, and then it moves every time I walk across. I won't feel alone anymore. So that's the plan. There are so many different things that we can do with this. So one of the first projects that I did that received data from Android is this sensor on my 3D printer. So my 3D printer is super basic, and it does not tell me when it finishes a print. It just finishes and then chills, right? So I really want to know when it's done. So what I did was, every time a 3D print finishes, the nozzle moves to the end of the line and then waits there. So I need to find out when it's there for an extended period of time. That's when it's done. what would I do? So the first thing we do is we want to read the data on Android first, right? So the Arduino senses like a bunch of information. It's basically sensor data across every couple of milliseconds. It's just like, oh yeah, you're 23, 24 millimeter away from me. So it's really, really precise. And I don't really need that much information. So I'm going to take the average of all the sensor information that we have. The most important thing about working with sensors on Arduino is to make sure you sample your data really well. When you have so much influx of data, it's really easy to go, I can do so much with this data. And that is true, but you also have to make sure you get exactly the information you need. And that's the hardest part in the Arduino world, right? So in this case, for example, again, we have the in endpoint, something that we found before. And then I'm going to take the last 5 readings that I got from the sensor and say, if the last 5 readings are the same, then it's close enough for me, right? So I'm going to go with that and then say, okay, if it's not close, I want to clear the byte buffer. I want to make sure that the new input that's coming in has place to be filled in. So I'm going to check if it's not close enough. I'm going to queue the byte buffer again and then check if the request, right? If it's not close enough, I won't do anything. And if it has remaining space in the byte buffer, I will just let it go because it can still fill up, right? But if it does not have any remaining space, I will clear this byte buffer, which is why in the beginning, if you look at the first line, we took the max packet size by 2. So we took that really big array and allowed it to be filled in by the Arduino. So this is what we're doing here. Now, when it's close enough, you open Spotify. Yeah, I had a really weird song on there, so now it doesn't link to anything. But it works. So that's what we're looking at doing. So we have our Android, right? We took the data, we sampled it, we looked at the last 5 readings. But on Android, I didn't do a bunch of it. Here, I'm doing a lot more sampling, right? So first of all, I'm going to check the distance, right? I'm going to see how far it is from my sensor, and then set up a control distance, right? Which is I'm going to first let it be in the same position for a really long time, take a lot of samples, and see what my control data is. And okay, that went by really fast. We're going to take a filter array here. Again, same thing. I'm going to take 20 samples in a really small amount of time, and then add all of my measuring to that data, to that array. So I have a lot of arrays here. And then I'm going to take the average of 5 to 15. I know this is kind of weird, but the first 5 and the last 5, I'm just disregarding them. So I'm taking the middle 10, and then I'm getting the average of it, which is giving me a good amount of distance for that entire length of time. So it's the average that I need. And so using this is what I'm going to send back to my serial, right? So that's what the serial.print is doing. It's going to print into the serial, which is what Android is receiving. So this is we're doing the same thing again. We're giving in the baud rate, beginning it, so it's connecting to the serial monitor, and then sending all of the data that I receive from the Arduino to the Android. Okay, so this is how it worked. Next steps that I have, number 1, Arduino with Wi-Fi. I mean, I had it already, but I did not want to jinx this. This was already quite jinxed with the demo. But that's the best way to do it. You can be far away and then control it with your Android. Of course, this is the best way to do it. Number 2, suckers. It doesn't really look like a tentacle, so it's just a purely aesthetic choice to add suckers to it. Number 3, we have, I also 3D print on fabric. You can 3D print on mesh, which is really interesting because the way 3D printing works is that it prints layer by layer. And you have mesh in between. What happens is the plastic on the bottom fuses to the plastic on the next layer. And so the mesh gets stuck in the middle, and so you can print on fabric. I have a really cute dress with cats on it that I printed. Happy to show it to you if you want to talk to me later. But I also want to make sure that that is something I can do with this, because then it makes the aesthetic choices way nicer. And so that's something I want to try out. Number 4 would be more segments. Right now, it can only do an S. But if we go up to 3, maybe 4 segments beyond that, I don't think it can bear the weight. Maybe more heavy-duty servos would work really well, something more expensive. So yes, I'm happy to try that out. Most important thing is Compose. I want to do more with Compose, see how much more data I can send through to the Arduino or how much more data I can get through, and show it in a more visually appealing way that I can work with. Okay, so just one last thing before we end. We talked about this. One segment can make a C, right? Two segments can make an S. Okay, so I have a question. If you get it right, if you want, you can take some of the tentacles with you. I'm happy to give you instruction and do some troubleshooting. Okay, so I have the shape. How many segments would this take? Yes. It's a little tricky. First come, first serve, so 14, okay. 6, okay. 7, okay, I have a 7. Any more numbers? So who said? Someone said a 5, okay. 6, another 6, okay. 9, okay. You're going down from a 14? Okay, all right. We have a 5, a 6, 9, and any other numbers? Okay, the actual answer is 5. It's nice to, yeah, congratulations. If you want a tentacle, you're welcome to. No, I mean, I can print a lot of them. This took me to, yeah. The way this works is that we have the single length, which would be a 1. The curve below it would be a 2. The whole straight line is a 3. It doesn't require 2 of them. One other for the curve, and then one from the straight line again. So that would be a 5.
This idea in mind, but it's kind of a stretch, but
yeah, it worked. Yes. Great. This is the QR code for the presentation, so you're welcome to it. I don't have a files for the prints yet because I want to make it more stable before I let anyone try it out. But I'm happy to share it on LinkedIn or Twitter when I'm ready to do it, or maybe at a future DroidCon. So yeah, thank you so much. I'm happy to answer any questions. Yes, please.
When you are communicating over USB, if you have a hub, for instance, will it see the hub as a separate entity on the list of the tree node, or the node of trees, or something like this, or it will transparently tell you about the devices connected into Android?
It will tell you about everything connected into the Android. Yes, you can actually see it here if you want to come by. So it will show you a list of USB devices. Usually it will give you what ports it's connected to, what vendor ID it has. You get a list of devices essentially. And on the devices, it will also tell you what kind of interfaces the device has. So it's a USB device object essentially that you're getting from the connection. Yes. Yeah? Yes?
Sorry, it's a 3D printing question, I guess.
Yes, of course.
You said about the discs
yes.
needing to be printed into parts. Why is that, and how did you, maybe I missed something, sorry.
Yeah, no problem. This one?
No, the discs that pull
the pulleys?
The wires, those things.
Yes.
Those things. You said
okay.
they need to be done into parts for some reason.
Yes. So essentially what happens with 3D printing is because it prints by layers, you want to print something with a bigger circumference, right? And then you want something with a smaller circumference and something bigger, right? That's how a pulley works. The idea with 3D printing is that if the height is long enough, tall enough, you can provide supports for that upper diameter to print without falling down, because then it doesn't have support. But with something that's kind of thin, it's really hard to do that. So I mean, you can look at it later, but it's basically, it has holes that I can just push and hold. Yes.
Like that.
Yes.
Okay, cool.
So it has the base and the connector into the servo. So basically the servo has a little holder that you can push into, and it has ridges on the outside. So that's how it fits in really well and doesn't slide alongside. So yeah, actually for most standard things like servos and motors and other pretty standard parts, you get the fittings, models for the fittings, and then you can add whatever you want to it. So you have the fitting, and then you can add a pulley, I can add a lever, I can add whatever I want to the outside of it. So it makes 3D modeling easier when you have basic parts already existing. Yeah, you can also do screws and like a bunch of other industrial equipment. You already have the models for them, and if you want to just use it, that's what you do. I did the same thing for the screws actually that are here, the screw holes. The outside of the screw, you can just subtract it from the cylinder. So that's what I did, and now I can fit in a M3 screw, a pretty standard M3 screw that you get for like. You can use a bunch of them. I started with Blender because I was familiar with animation, but it's not the best for most mechanical usages. Because if you want to make something like, I don't know, D&D figurines or something that has more aesthetic shapes, then Blender, yes, is an amazing option. If you want something more geometric, I think using things like AutoCAD or Shaper or
Is that Shaper, is it?
This is Shaper, yes. Shaper is an iPad app. It's also on Mac. It's pretty easy to use. It's free for a couple of files. You can always download them and then reuse the files. So that's always an option. I also use. Sorry. No. What I do like using and started recently is Autodesk Fusion 360. That's actually a really good one. Fusion 360 is free, and the geometric help on that is much greater. And you can also have history. It's like Git history, which makes it easier. Shaper doesn't have history. So when you have history, it's really easy to be able to go back and sort of change numbers. Just make it bigger or smaller. You want to not go back to the very beginning. So it's really helpful that way. Yeah? Yes?
More of a curiosity, did you run into any energy issues with the number of things you plug it into the other?
Not yet. The Arduino is just like usually 5 volts. I mean, I put it into V input, but even if you put it into 5 volts, the servo should run fine. And anyway, our Arduino Uno has a limit of, I think, like 12 or 13 inputs, 14 I think, including the